All right, let's get started. So I'll be talking about the SCION Future Internet Architecture and tell you about the journey that we've had working on this over the last 13 years. And so I guess in this audience, I don't need to talk about much about the all the shortcomings of today's internet. Fact that there's a lack of sovereignty of communication, many outages, DDoS attacks, routing attacks, and so on and so forth. So I'm assuming people are very well aware of a lot of the issues that we are facing in today's internet. There's also ransom attacks and ransomware, or ransom DDoS attacks, which essentially the one is attacking with a DDoS attack in order to shut down network connectivity and charging money for this. And so we've seen a number of such attacks, and they also are on the rise. For the importance of availability, I'm also assuming that many people are well familiar with the Facebook outage last October, where there was a 6-hour global downtime of Facebook, Instagram, WhatsApp, which actually started with the border gateway protocol, where a management system withdrew some routes, so the DNS was not reachable anymore, and then cascading failures occurred, and the entire infrastructure was down, including door locks that didn't work anymore, doors that didn't open anymore, so people couldn't get into the data centers to fix the problem. So I hope everyone agrees on the importance of availability. So given all these issues, and they're not new, they actually, many of these issues go back as far as the last millennia, when I started my PhD in the late 90s, where BGP hijacking, etc., was already a known problem. And also issues of BGP convergence were already a problem. So trying to fix this for many years and fixing these issues have led us back in 2009 to start thinking about a fundamentally secure and fundamentally robust network infrastructure. And so over these 13 years now already, we've assembled and gathered many interesting insights that I will share with you in this talk, where we'll show these kind of slides with these pathway in the forest to show you the nice aspects that we've discovered on this journey. So of course, when we started in 2009 thinking about new internet architecture, we wanted to make sure we took into account a lot of the excellent work that was done before, and we took specifically inspiration of a number of projects shown here on this slide, and drew inspirations from all these works. So the architectural principles of the SCION architecture that we started to work on essentially include the following aspects. So first, having a stateless packet forwarding, so trying to avoid as much as possible state in the network, because a state causes and has many issues associated with it. One is that it may be inconsistent, and the other one is that it may overflow. So we've seen adversaries overflowing BGP forwarding tables and causing outages in that way. And especially from a security perspective, if you do not have perflow state or much state, there's much less opportunity for any inconsistency. And so all the protocols that we've been working on, we try to make sure we don't have, or we can avoid state as much as possible. The routing system, and in particular here, we're talking about BGP, the border gateway protocol. So it's about inter-domain routing and not intra-domain routing. BGP has a lot of convergence issues in the sense that it converges very slowly. And that has been a well-known problem for over 30 years. And so we know that in order to achieve high availability, we wanted to make sure that we have a routing system that converges in a way instantaneously. So there's no, in a way, no convergence phase for the routing. Other important aspects include multipath communication and path-aware networking, which is to say, in path-aware networking, the sender knows and can select among several paths, and then knows exactly and achieves transparency where a packet will go through the network. So, of course, the whole architecture was designed from a security perspective, and we very early on worked with formal verification systems to achieve strong properties for the security of SCION. Sovereignty, transparency of trust roots was another important aspect that I'll get back to in a few slides from now. So when you look at different properties, security properties, many people think about secrecy, of course, that a network should provide secrecy, but today that is achieved primarily through a system like VPN, end-to-end encryption, but also instead for a secure routing infrastructure, the main property we want to achieve is the one of availability, so that an adversary cannot disrupt communication. So say through DDoS attacks or routing attacks, or injected failures and so on, kill switches, they should not be possible or be very quickly recoverable. So sovereignty is another important aspect. So meaning that we can locally operate the network and we don't have any external dependencies, and as well as transparency in general to enable transparency of trust roots, who needs to be trusted for each operations, but also transparency with respect to paths and so on. So in terms of secrecy, SCION is not primarily contributing to that, except the aspect of geofencing, which enables ensuring that traffic stays within a certain area, and in particular does not flow through certain autonomous systems. That helps also secrecy, as even encrypted data that is being observed can be used to extract information. Right? So that's, for instance, website fingerprinting is a well-known problem, but also many other ways can be used to extract information, even though all the traffic is encrypted. So here is a first insight. So maybe this is very obvious, but just in case, I'd like to nevertheless highlight this. So when you're building a large-scale distributed system, then formal verification is absolutely required if you want to achieve strong security properties, right? So as humans, we design systems, but it's impossible to think through the billions, trillions, and many different states the system can be in. And so only formal verification can give us strong assurance that these systems actually do provide their security properties. And so we very early on worked with David Basin's group and Peter Miller's team in the Verified SCION project to formally validate and verify the different components of SCION. Where David Basin's team worked on the protocols and Peter Miller's team is working on the source code implementation and to verify the source code to ensure also that it matches the specifications and the protocols. So when we started working on SCION, the first aspect that we wanted to resolve was actually an aspect of sovereignty, and this means that through the observation that in the world we cannot agree on the same trust roots, the idea was to have and enable definition of trust roots purely locally. So here we see isolation domains, and they essentially group autonomous systems. So an autonomous system would be like ETH Zürich or company like Swisscom or Deutsche Telekom would be one of the smaller circles here. And so they group together into areas that can agree on the trust roots. So this TRC, trust root configuration, this indicates the roots of trust that are that need to be relied upon for cryptographic operations within that isolation domain. But again, it's a virtual construct, so to speak. So it essentially is a grouping of these autonomous systems that can also be overlapping. So an entity in an autonomous system can be part of multiple isolation domains to achieve this level of sovereignty. Then we have some of the autonomous systems. They're typically the largest internet service providers, or ISP, that are within the isolation domain. They govern the isolation domain as part of what we call the ISD core. And so they're the core autonomous systems. So they're the ones that are then also representing the isolation domain through their cryptographic keys, and they also manage the cryptographic keys. So I'd also at this point like to point out that there's a separation of general public key infrastructure for TLS, let's say, and this public key infrastructure in SCION, which is purely based or purely focused on the availability. So these keys are not being used then for end-to-end, establishing end-to-end encrypted communication, but this is really for the availability of the entire infrastructure for the routing system to authenticate messages and so on and so forth. So it's not, it's essentially high availability public key infrastructure, purely for routing. And so it turned out that this structure of these isolation domains also was useful from a scalability perspective, because as I'll show in a minute, there's a routing protocol finding paths between the isolation domains and then finding paths within an isolation domain. So that, it turns out, also has excellent scalability properties. So here's a high-level overview in one slide. I'll then show a few more slides with a bit more detail. But but here's the one slide overview of SCION. In essence, the routing plane, or the control plane, finds path segments. So it finds two types of path segments, one within an isolation domain, and then path segments between core ASs, and that we call core segments. And then the control plane also assists in disseminating these path segments. And when one wants to communicate, for instance, a host in F wants to communicate with the destination S, the host looks up these segments and then combines them. And in this example, there are only two different possible end-to-end paths that can be combined. And this information then also goes into the packet header, and the packet traverses then the network along these autonomous systems. So as a result, the routers on the path are actually very simple. They don't have intradomain forwarding tables. They simply look into the packet header, verify cryptographic information, and then send the packet on towards the destination. Now, a bit more detail on this, this path construction that we call through a process called beaconing, works through these path construction beacons, or PCBs, that get sent out. They're sent by core ASs and then traverse the network, drawing the path segments towards the destinations. And so each core AS periodically performs this operation, and all the other ASs forward these path segments or path construction beacons to create these path segments. And so receiving such a beacon message then already enables communication, as this is the path segment that can already be put and placed in a packet header to communicate with ASs along these path segments. Now, what's really exciting is that an entity can now, or an AS can look at these different path segments and decide which ones it wants to communicate with its own hosts. So in this example here, there are 4 path segments, and they're called up paths because they go from an AS up towards a core AS. And one can decide which segments to send on to its local hosts. In this example, all the 4 segments are being made available through a path server infrastructure. And for this, you can imagine infrastructure similar to DNS, where end hosts can query for paths and receive these paths similar to DNS infrastructure. What's also really exciting is that the ingress path control can be controlled, so meaning how others can reach destination AS. And here again, we have these 4 path segments that S registers at the core path server in the AS core. And in this case, it deleted one of the path segments that it did not want to make available to the world. For it could be that it's a very good path, or maybe, and so a very good path that it only wants to keep to select entities to communicate with it, or it's not a great path, and so it does not make this path available globally. But the other 3 paths are being made available, and so if one wants to communicate with this destination AS, these paths would be the ones that are being communicated when one performs a path lookup. So here's now an example of communication inside an isolation domain. So for instance, the 2 entities from R to S in this example, R wants to send a packet to a host in S, so it looks up these path segments, and it obtains the blue up path, the green down path segments, and these 2 orange core segments. And they can now be combined in different ways. So this first yellow path that is possible is called a shortcut path. That's a combination of a blue and a green path that they intersect at O. We're also using a peering link between O and P, similar to peering links in today's internet, or going all the way up through the core ASs. That's also possible. So in this example here, we have 4 different paths that can be used, these 4 yellow paths. And again, there's no state in the routers. They can all be directly used. And this works very similarly also on a global basis, where S wants to communicate with E prime. And so it can make use of different path segments and combine them in different ways to achieve, for instance, these 3 yellow paths. Now here it's not too interesting because all these paths have a lot of intersections. Their disjointness is quite poor. So traditionally, we would, and we also observe this in today's internet, that there's a lot of different paths available that then actually multiple disjoint paths can be used. So before I talk a lot about the advantages of SCION, let me briefly mention some of the drawbacks. Here, the first drawback is the latency inflation when you start sending traffic, because initially the destinations registered path segments and also the core path segments need to be fetched. And so that requires additional time. So when a host wants to communicate with the destination, it first performs a DNS lookup. From the DNS lookup, it doesn't only receive the address, but also an isolation domain and an autonomous system number. And then based on that, it needs to look up the path segments, which require additional time to fetch, of course. And so one cannot just send the packet right away. But for the most part, these paths will be locally cached. And also this additional latency initially also can be amortized, because in SCION paths can be optimized, and so some of this lost time can be regained. There's also additional bandwidth overhead due to this information in the packet header. On average, there's about 80 additional bytes needed to encode the path segments, which is not little, but it's also, I guess, not too much. And then, but this information is needed to get all or a lot of the advantages, right? So when you need this path control, simpler data plane, that's essentially the price that we need to pay to get all these features. There is increased complexity in key management. The control plane is using digitally signed messages to authenticate path construction beacons and also to set up secure connections and so on for the control plane purposes. And so there is a key management effort. And however, the point here is that any highly secure or any secure communication infrastructure will need to rely on cryptographic mechanisms for protection. And so there will be a need for maintaining keys and in any secure infrastructure. There's also higher setup cost for SCION, and that's actually the highest monetary cost, which is to educate people, individuals to make use of the new architecture. And so there have been ways to simplify the deployment, to automate as much as possible and so on, to reduce this. But if you look at the total cost of rolling out SCION in an AES or in an ISP, that's typically the training of the employees. All right, so maybe this is a good point to ask some questions before I go through the next slides and we're talking about these. Does anyone have a question at this point?
Does anyone have a question? So maybe I shortly ask before the others ask. Actually, I had a question. So so it sounds like deployment actually would mean that, let's say, if I'm in a AES and I control resources, then I need to set up a zone for the passes like I have now, a zone for reverse DNS. I will also maintain such a zone on my DNS. And this will allow everyone else to query to ask how to reach me, right? And I need to set up routers that are capable of querying everyone else to be able to compute the path. So if I want to deploy this, there are two aspects: how the others reach me and how I reach the others, correct? And so if I set up now SCION routers, which can speak SCION.
Actually, sorry, it's not correct. Quite.
Okay, so can you connect me? That was my question.
Right. Right. So deployment actually is all one needs is a SCION border router and a path server. There's also certificate server. And they all essentially run as a service on a workstation. And that's already it. And then, of course, also SCION connectivity, which is already offered by a number of different ISPs. And we try to avoid, if possible, going over today's internet. So the today's SCION production network is not an overlay on BGP, so it doesn't rely anywhere in the world on BGP. And so you essentially would need to get one of these border routers, which is open source source code. So you take a Linux box, set up this border router, and then get this SCION connection, which you can do actually through either at many data centers, they already have someone running SCION, or you get a layer 2 connection to the next data center that has SCION connectivity, and that's where you would connect to an ISP offering SCION. So it's quite easy. So there's no, for DNS, no, I mean, we have different deployment ways to deploy, and so there is no need to set up any specific aspects in DNS. But if you have, say, a web server from which you want to natively serve SCION content through the SCION protocol directly, then you would need to add information in the DNS with the isolation domain and the autonomous system number. But other than that, it's really at the limit a single machine that you set up that runs the router and all the services on this one machine, and that's it, right? And then all the entities, all the hosts in your university will be able to make use of SCION already.
Okay, thanks. Now we have another question from Marcel. Okay. Marcel wrote that PaaS server would mean more centralization. How is that server secured against attacks or political influence? Right.
So these PaaS servers are distributed. They're in each autonomous system. And the core ESs store the path segments of the downstream hosts. So it's quite a distributed infrastructure. And we have ways to protect messages to register path segments and also to fetch path segments. And so that prevents also DDoS attacks on the whole infrastructure. We've documented this in the new SCION book. So not the old book from 2017, but the new one that just came out. And there it's chapter 10 and 11 contain a lot of detail how also the different infrastructure elements are being protected and how the SCION traffic within an AS is also protected against IP level attacks, where somebody would inject a lot of IP traffic, and how then the SCION traffic can still be protected, even though it shares the same links as the IP traffic, of course, within an ISP. So it's a longer answer to explain all the details, but if you're interested, right, please take a look at the new book, which, assuming your university has a Springer Springer subscription, you can easily download it and see that. Does that answer the question? Or?
Yeah, apparently it did. Thank you. So I think these are all the questions at this stage.
Very good. All right, so let me talk now about advantages and deployment aspects. So an exciting result is the scalability of SCION. And here we compared to BGP, and we compared different autonomous systems for which we had real world BGP information, and then we simulated in the same network how much work SCION would have to do. And we see on the left-hand side that the overhead is only about 10% of what BGP's overhead is, even though the system finds on the order of 50 to 60 paths. I think here we cut it at 60 paths and didn't create more. So despite finding a very large number of different paths, the overhead is only 1/10 compared to BGP. And it looks even better if you compare to BGP sec, which you see on the right-hand side. And here it's normalized again for different autonomous system instances of very different specific ASs in today's internet. And we see that SCION has a massively lower overhead than BGP sec, which is on average about 5 times more expensive than BGP. So we've found in this study that SCION has about 200 times lower overhead than BGP on a per path basis, and about 1,000 times lower than BGP sec. And also the time to connectivity is much faster because there's no convergence process in SCION, that essentially once these beacons are sent through the network, connectivity is almost instantaneously established. And so one doesn't have to wait for the network to converge in the same way one has to wait in BGP. So this was quite exciting. Now, what's important is how can we use SCION today? And obviously a new internet architecture is challenging to deploy. And there's a number of different mechanisms that have been that we worked on over the last years to simplify deployment. And here we see for the different methods in green, what would not need to change, and in red what would need to change. And so we see one specific approach which will be presented at Usenix Security this year, where we show how we can make use of SCION to protect today's internet end-to-end communication. And that's an approach called SBAS. So I'll briefly talk about a few of these methods. And as you see, in many cases, we don't have to change the application or the operating system. Actually, the operating system doesn't need to change for any of the systems. So one can install simply an application and already take advantage of SCION properties. Most of the cases, if the local autonomous system also supports SCION. So for the ISP, as we briefly discussed earlier, there's actually not much work to do except setting up the routers, training the employees is probably the biggest overhead, and setting up connectivity with other ISPs offering SCION. And so there are today about 12 ISPs already that are SCION enabled, with more coming. And so this is actually a relatively lightweight operation for an ISP. At the end domain, also it can be simple through a system we call SCION IP Gateway, or a SIG, which takes traditional IP packets and then converts them into SCION packet if the destination is reachable via SCION. And this does not require any upgrades on end hosts or applications, and still can give you many of the benefits, not all the benefits, because the ultimate benefits you get when the application is directly enabled and can then do a path selection that is very specific to that application. So the SCION production network has been growing. Mainly, this growth was mainly led by Anapaya Systems, which is a startup commercializing SCION technology. And what's really exciting is this global network is BGP free, so it does not have any dependence on BGP. So you can today, when you obtain SCION connectivity, have a completely fault-independent system for communication, fault-independent from BGP, and vice versa, which is of course very useful. Can be very useful to have. So there is global connectivity available already today, where an ISP called InterCloud, for instance, is selling SCION connectivity, and they have connectivity to over 180 data centers globally, which is a large footprint already, offering SCION connectivity in all the major metropolitan areas in the world. So one project that I mentioned earlier that requires almost no changes at all to make and benefit from SCION is a project called SBAS, Secure Backbone AS, which was in collaboration with Princeton University and University of Virginia. And here we looked at, and this is the paper coming out at Usenix Security next. Actually, it's in a few weeks. And so here we essentially looked at how can we optimize regular internet traffic, optimizing, for instance, latency or CO2 or security in a way that we can take advantage of the SCION network without changing much in today's internet. And the approach essentially is that we set up SBAS points of presence around the world. They're shown, the two nodes are shown in green here, that then make use of the SCION backbone to optimize network traffic. And for this, one of the two sides, either the sender or the receiver, need to opt in, and then they can essentially optimize for a certain property. And then the SCION network is being used to optimize. So in essence, the SBAS system speaks BGP and is announcing the address ranges that are reachable by this SBAS system, and is announcing them at all the POPs globally. And when the packet comes in for that destination, or when a source that participates wants to send a packet, it also sends to a POP, and then the SBAS system optimizes based on the sender's or the receiver's property, for instance, providing a hijack resilient, BGP hijack resilience. And that's also the main story in the paper that's coming out. But also you can optimize for greenness and select paths with lower carbon footprint, or also paths with lower latency. And if the SBAS system notices that today's internet has better performance or better features, then of course it also sends the packet over the regular internet without using the SCION optimization. So it's quite an exciting project, which neither the sender nor the receiver really needs to be aware of SCION, except one of the two sides needs to opt in into the service. So the IP prefix can be globally announced and can optimize its traffic. So very, very easy to use, very lightweight for deploying and taking advantage of SCION properties already in today's internet. So an exciting aspect also is the fact that incremental deployment is quite feasible, right? So when we started with this project, of course, initially, we didn't think much about that we're going to work so long on this. We just wanted to see how secure an internet infrastructure could be. But over time, we found out that actually it is quite possible today already to deploy a future internet architecture operating side by side with BGP and essentially reusing local connectivity, essentially reusing local IP connectivity in a way as a layer 2 protocol. And so it's required much less effort to create a global BGP internet or a global network that is BGP free and operating side by side with this. And so this was a big surprise actually in retrospect, because initially this always seemed like an unsurmountable obstacle to actually deploy a future internet architecture. So there are lots of resources you can look at, and I recommend you to take a look at the new book, which has a lot of details also on the DDoS resilience that are only published in that book. And so lots of resources to learn more about SCION. There are also a lot of extensions like secure time synchronization system and secure PKIs and so on that you can use in conjunction with SCION that I won't have time, unfortunately, to cover. So there's also an association we're launching right now that works with all the entities with efforts in the SCION ecosystem to further research and also work with vendors, integrators, users, and ISPs to harmonize and work on this ecosystem, as well as working out the standardization, certification, and so on. That's what the SCION Association is doing. And so we're in the process of launching this as we speak. So in summary, SCION is an architecture, next generation internet you can use today. It's also high performance, not only high security, because the path-forward network offers enhanced efficiency, multi-path communication, enables also increasing the available bandwidth, and of course, different aspects of the architecture provide a lot of security properties, including, for instance, secure error messages and so on. So each aspect of SCION is designed from a security perspective to avoid a lot of the problems that we have in today's internet. So with this, I have also second part of the talk. I don't know how much I can get through, given the the time already, but I'd like to spend maybe 10 more minutes and tell you a few of the exciting aspects how SCION can be used, and to talk a bit more about the security aspects and also a bit more about the multipathing. So the claim of SCION is that you can, if a benign path exists, then the sender can actually find this path and use this path with some amount of minimum bandwidth guarantees, which depends on the path, regardless of the adversary that is outside the end-to-end path. So there are a lot of challenges that need to be addressed in order to actually achieve this property. Again, in the book, we have the details how these properties are achieved, but let me give you some intuitions and some of the aspects that we've been working on to achieve this property. So first challenge in this space is that the adversary may inflict routing instabilities or misconfigurations that then will prevent you from being able to use the end-to-end path. And so here, observation is that you need stable forwarding and multipath to avoid these kind of problems. So if you have a single path forwarding, you cannot achieve strong availability properties, because when you have, for instance, protocol convergence phase, like in today's BGP, then no path may be available for the time during which the system is converging, or an equipment failure will result in unavailability. Or if a forwarding path experiences high packet loss, then a practical application cannot make use of this. And so a single path system essentially has these fundamental challenges. And so if you have stable forwarding, where you can always use a given end-to-end path, no matter what happens in the control plane, gives you already very strong properties, but also multipath that enables you to make use of backup paths or different paths in case your main path is not working. So here's an example of today's internet where you have a specific problem with the single path routing. So in some cases, BGP switches to a path that has too small a bandwidth, and then results in a bottleneck. And so there's a lot of packets that get lost, and some applications then lose connectivity. But since connectivity still exists, BGP doesn't always move away from this path. And so we've seen examples where outages then persisted for over 30 minutes because the need of this manual intervention. And there's some really large-scale problems, large-scale failures that happened exactly due to this issue of a path that was operational, but had very high packet loss. And so BGP did not switch away, but it was essentially unusable for all the applications trying to use it. In a second example, failed routes are not being withdrawn in some cases. And so the failed route continues to be announced, and then a lot of traffic is coming in without the entity receiving it being able to deliver it because of the failed link. And so we've seen in one example of CenturyLink where this caused a very large-scale outage, and that's another problem. So essentially the insight is, if you have a secure protocol like secure BGP, you did not solve these two last problems I just mentioned. So it does not solve the issue where BGP picks a path with insufficient bandwidth, because that's maybe a legitimate path. And also it does not protect from the case where a failed path is not being withdrawn. So even a secure routing protocol will not enable you to solve these two issues. So you really need path awareness and multipath to solve these problems. And so you need a native multipath intra-domain routing protocol to solve these issues. So But multipath and path awareness also has a lot of performance advantages. So here's an example where we send a packet from Europe to Southeast Asia, and typically it goes through the US on this path. And even though there's a much shorter path going through the Suez Canal, for instance. And so BGP being a money routing protocol, it just picks the cheapest path. But actually in this example here on the map, we see the red path is typically a higher bandwidth path, and the green path is a low latency path. So they're both good paths, right? It very much depends on your application requirements if you want to send traffic on the green or on the red path. And so ideally, both paths are available. And so you would then pick in your application about which path to make use of. Now, this multipath, when you actually experience it, it's so exciting that it's hard to go back to a single path internet. So it's similar as when you fly and you get upgraded to, say, business class once, and it's hard to go back to economy class thereafter. Or you drive an electric car and you see all those advantages of those EV vehicles. It's hard to go back to legitimate or to traditional ICE vehicles. And so in SCION, it's similar, and we observed this with people starting to make use of SCION, that they see all these different path choices, how that provides them with a lot of advantages. So in this example here, we see end-to-end communication going over a number of path segments that can be combined. And in this example, offering 54 different end-to-end paths. So it's really, in SCION, you can get a very large number of connections. And so you can see that having a lot of different paths, you can then optimize for, say, latency or jitter or bandwidth, or also privacy. In a sense, you can avoid certain ASs or CO2 footprint and so on, which is really, really exciting, offering a lot of opportunities for optimizations. I see the time is pretty advanced, so let me not go through all the following slides. That was an example of a video which uses multipath and which can then very quickly switch paths in case one path experiences lower quality, essentially with which essentially provides a very high call quality if something fails. And so the insight from all of this is that multipath is really a necessity. If you want to achieve high availability and performance, it's really not a luxury. It's really great when you have this available. And so I wanted to thank especially the whole SCION team, which has been working on this project for a very long time. We've started in 2009, and more people are joining the experience, and I hope also some people on the call would be excited by it and perhaps say, let's also get a SCION connection at our university, which through DFN that is actually possible. And you can then get a native SCION connection at your university and communicate with everyone else who is on the SCION network, which offers a lot of exciting also research opportunities. So with that, many thanks for your attention, and we hope to have some time for questions.
Adrian, thank you very much for the very interesting presentation. Does anyone have questions? Good, then maybe I start. So my question that I asked you before, that was actually, you answered it in the second part of your talk, where you said that networks to connect, they need to install routers. And I just jumped a little bit with my question. So what kind of routers do they currently use to connect to the SCION network?
Right.
On the backbone, I mean.
Right. So there are software-based routers. They can push 100 gigabits today. And there is also Extreme Networks has enabled a line of their routers to become SCION aware. But there also it's a software-based solution. So the performance it's not yet comparable to traditional hardware routers, but you know, that are pushing several terabits per second. But given the the early deployment now, the 100 gigabits per second per on a using a workstation, also price-wise, is offers building one of these networks and setting up this network at low cost. Right.
Yeah, right. So do they use hardware acceleration? Because I with software routers I could achieve 10 gigabits per second.
No, this is purely in software, so without hardware acceleration. So we actually believe that long term, as hardware support becomes available, that switching will be even faster than in today's network because of the simplified forwarding plane. Right, you don't have the longest prefix match operation anymore, which can be optimized quite easily for IPv4, but for IPv6, where we have a very large address range, becomes again challenging to optimize. And so the AES, so forwarding a SAN packet essentially takes an AES operation, which can be done in a few nanoseconds in hardware. So it's really, based on our calculations, even the energy required to forward SCION traffic will be lower than today's IP traffic.
It's really cool. Thanks. Anyone has questions? Good. I guess we have no questions. I would love to discuss a lot of these topics with you, but I guess we can talk about it sometimes when you get better. If no one has questions, we will then sum up and close. Last chance for questions. One, last chance for question two, last chance for question three. Yeah, Adrian, you want to say something? Do you have a question?
I wanted to say it's really quite feasible to set up a native SAN connection to your university. So I hope we can do this, because now we're building a global educational network, which is, of course, part of the SCION Internet, SCION production network. But specifically, we're connecting different universities around the world. And with SCION, that we're currently SCION enabling, and also the ATHENE participating, it's particularly easy to achieve and create a SCION connection in Germany at any German university. And so this would also allow exciting security research to compare with today's internet, being able to use the native SCION network. So this is not SCION Lab, which is an overlay network, but really a native the global SCION production network. And so it's also very high speed and in terms of latency and so on and so forth. So it's quite exciting, I think. And so I hope we could also set this up and you could make use of it for your research as well.
Yeah, so that would be very exciting. So actually, you know, we are building a platform for research purposes, but also for practical purposes like identifying, detecting, or blocking attacks, and not just attacks on BGP hijacking, but different types of attacks, denial of service attacks, and others. And for this, we are purchasing ASs and prefixes. We have already, and we are setting something also up like peering platform. So that would be definitely interesting to see that. And on the university side, I think it would be definitely interesting, but it may take a bit longer at the moment. So with this platform that I told you, we do plan to do a lot of research on security. So I think that would be very interesting for us if if this is interesting for you.
Right. So the interest would be that you could make use of both. So you could use the traditional internet, or you can make use of the SCION network. And with if you're announcing things via BGP, I think what's exciting is this interaction also with this SBAS system, right? So there we also have an AS, and we're also announcing these IP address ranges, and so we could, join forces there and announce each other's prefixes to get better connectivity. And then the SCION backbone will give you another independent routing plane to get the data from the POPs where it comes in to your end destination, in case it gives better performance. The internet, that's something we're observing, that the internet really, in terms of latency, is can be beat actually in sometimes we observe 30% of the end-to-end paths if they're far enough. Sometimes even higher, up to 50% of the end-to-end paths, just to indicate that the internet actually has much lower performance than we think it does.
No, I definitely agree with you, and it's interesting. By the way, to your comparison, to your metaphorical comparison with the first business class and the economy class, they both arrive at the same time, unless you are referring to the time that it takes the economy class to leave the plane. But
No.
I think you meant the latencies.
No, the comparison is you have a choice today between using SCION and the today's internet. And once you experience SCION, which I'm referring to the business class, you wouldn't want to go back, right? Once you have this option of having multiple path choices and also having more path transparency and all the security mechanisms, you wouldn't want to go back to the economy class, because it's of course much nicer to sit in business class. So that was the comparison. That was not a speed, or also not in the car case. It's not a speed issue there, but just a nice to have issue, right? It's and sometimes you have to experience it to feel the advantages, and then once you feel it, the point is it's hard to go back once you've experienced it.
Now, I'm convinced, absolutely. So, we're working on relevant topics. We're doing attacks against BGP to make it more secure, and actually coming up now a new attack that we have against RBKI. So I think it definitely fits to explore cooperation on this aspect. How can we do research on SCION and use SCION also for research and for improving current security? So congratulations on your Usenix papers, and enjoy Usenix, which is coming up, right?
Great, yeah. So looking forward to chat more.
Okay. So if no one has questions, then thank you very much for your presentation. It was extremely interesting. Thanks for explaining SCION to us, and look forward to see you in the near future.
Likewise.
Thank you. Bye-bye.
Thanks so much.
Bye, everyone.